Hi, everyone. Thank you for joining us today. My name is Elizabeth Winkler. I am the Director of Product Management here at Anaconda. And we're very excited today to talk to you about cloud native data science. And before we get there, a little bit about Anaconda. We are the #1 machine learning enabling platform out there. You may know us because of our open source solutions, which have 6 million plus users for data science in Python and R. And I am joined today by Mathew Lodge, who's our SVP of Products and Marketing. He's actually the best person you can think of to walk us through how to do cloud native data science.
Welcome to Cloud Native Data Science. My name is Mathew Lodge. I'm the Senior Vice President of Products and Marketing at Anaconda, and I've been in the industry over 25 years. I had an interesting career in technology, starting out by connecting countries to the internet in the early 1990s, and then I've worked for a number of large and small companies. I was also a governing board member of the Cloud Native Computing Foundation, a project of the Linux Foundation in 2015 and 2016. So I'm happy to talk to you today about cloud native data science. The fundamental problem in data science is how to go faster around this loop of discovery. So you can think about data science as starting with collecting and cleaning the data, maybe using visualization to figure out what you have, what's the shape of the data, what kind of things can you see within it. And from that, building a model, testing that model to make sure that it functions and performs the right predictions, perhaps, for a machine learning model. And then moving into deployment. So deployment is new in the world of data science for machine learning, because in the past, the output of data science might be a report or a spreadsheet, a dashboard, that kind of thing. But today, machine learning models are active software components as part of larger systems. And I'll talk about that a little bit later on. So we have this deployment step where you've got to get your data science to a place where it can be used by other people or other software inside your organization. So the quicker that you can go around this loop, the faster you can innovate and iterate and improve. Try new things, improve your models, reflect the latest changes in the data that you have. So cloud native might sound like it has to run in the public cloud at something like Amazon Web Services or Azure or Google Cloud. But cloud native is not a place, it's a way of doing computing, and it's essentially an architecture or an approach that's based on the way that Google, Netflix, Amazon, and the other cloud scale companies operate today. So you can be cloud native and run cloud native applications inside your own data center, and of course you can run them at public clouds. It's not one place or the other. In fact, cloud native really means three things. First one is the use of containers, so Docker containers as the unit of isolation and scale, and I'll talk about what that means in a second. API oriented means that the application is loosely coupled components that talk via APIs, network APIs. This is not a programmatic API as you might be familiar with in the Java world, where an API is basically calling a Java function on an object. We're talking about network-based APIs, REST APIs in a distributed system, and I'll talk about that in more detail. And then the third characteristic of cloud native is that the application is dynamically orchestrated. So these loosely coupled applications, this collection of components that talk through network APIs, enables the application to become dynamic and organic. So as demand increases on the application, it can grow in size. And as demand fades away, it can shrink back down again. As the application changes over time, new capabilities are added, the application grows and shrinks. So applications become almost organic, right? They adapt to the circumstances, they adapt to changes. So cloud native and DevOps, which is another aspect of cloud native, more of the operational and organizational side of things, these two approaches have been used in software development quite successfully for the last few years. And so Puppet Labs does a survey every year. This is from the 2017 State of DevOps report that they produce. And they look at the differences between leaders and laggards. So when companies respond to Puppet survey, they self-categorize. Are you a leader in the application of DevOps, or where do you consider yourself in terms of maturity? And so the difference between leaders and laggards in terms of responses is that the leaders are much faster and are able to do much more frequent deployment of their applications. So they're able to go around that loop much faster. They also get much faster mean time to recovery, MTTR. And it's not that they have inherently more reliable hardware or anything like that. It is the fact that they are able to respond much more quickly that means they're able to fix outages and fix problems, repair them when they occur. And so that leads overall to more robust applications, and that gives them a lower failure rate. So how can we take some of the advantages that you see here for cloud native and DevOps and apply those to data science? So cloud native, we said, was container based, and by container what I mean is a Docker container. Although it is possible these days there are competing container runtimes other than Docker, but Docker definitely remains by far the most popular container runtime there is out there. So a container has the application itself, the code, plus all of its dependencies. So a container image is really just a collection of files. It's called an overlay file system. So inside the container, that file system was applied onto the underlying file system of the server. So the operating system, Linux, though of course you can also use Docker with Windows, but today the most popular platform for deployment is Linux. The container files are essentially overlaid on top of the operating system file system, and that is the environment that the container runs in. So the advantage of a Docker container is that it's repeatable and it's standardized. When you run the container, you get exactly the same thing every single time. That makes it predictable. And it starts in seconds. It's an operating system level construct. You can start a container 5 seconds or less. And containers scale out rather than upwards. And I'll talk about this in a second. But essentially, once a container is running, then you don't change it. You don't add memory to the container, you don't add files, you don't expand storage. You add more containers in order to get more scale. And you might hear people talk about this as being immutable infrastructure. What they mean is that once the container is running, then you don't change the container. If you need to make a change, then you start a new container. I'll explain that in a second. And then a final point for the folks who are familiar with the Hadoop and Spark world. In that world, there is the notion of a container in Yarn. This is completely unrelated. This is a Docker container. So how do you build a Docker container? We use a Docker file. It's kind of think of it as the recipe for building the container. So the Docker executes when you do Docker build. It will run this file and follow the commands inside of it. And so here's an example for someone building a container with the latest Anaconda in there and installing their code into it and putting that into a virtual environment, a Conda virtual environment. And you can see that we start with a base image. They're starting with our mini Conda image, and then they're installing the additional things that they want. They're adding in some additional code, setting a few environment variables, temporary directory, running commands. And so when Docker follows all of these things, what you end up with at the end of it is a Docker image that represents the state of the container at the end of this recipe. So how do we use the containers? Well, we said that Cloud Native is essentially API oriented, right? So the containers are going to implement our API. So what does that look like? Well, think about applications the way they used to be written before the advent of containers and sort of Cloud Native architecture. You had an Apache web server on the front end. You had a blob of code that implemented the entire web store, in this example, a web application. And then we had a relational database on the back end, and that was your persistent long-term storage. So requests would come in from browsers, it would hit Apache. Apache would then basically pass a request into your code base, and then you'd have different functions, modules, whatever, that would implement the different parts of your application, like the store and credit card processing and inventory and so on. With API-oriented, what we do is we break the application down into individual components, and those components talk to each other over network-based APIs, like REST APIs. And so what this means is that now each of the teams that work on that application can work on their own individual component without having to wait for other parts of the application. And the previous way of doing things, the entire application had to be written in the same language because you had a single code base. And if you made a change in one area that could ripple through and affect just about everybody else, so you ended up serializing a lot of changes, and teams could not work independently very easily. And that's produced lots of challenges with the speed of updating the code base. But if you don't have a single code base anymore and everybody maintains their own, the only thing that will break other people is if you change the API. But if you're not changing the API and you're just updating the code and making it more effective, then you can iterate at your own speed without reference to the other folks. It also means that now, for example, that data scientists can produce components that can be used as part of the application, and they don't have to be all written in the same language. So we can see here in this example, we're using 3 languages. We're using Java, but also Python and Go. And the recommendation engine for this particular web application can be written in Python. And it can be self-contained, and data scientists can maintain and update that recommendation engine at their own pace, using their own tooling, using Python, R, whatever languages they want to use. And it integrates with the rest of the application. The Java developers don't have to know anything about Python. They don't have to maintain that stuff. They don't have to do anything special. And same for the Go programmers and so on. The other thing that we see here on API-oriented applications is that now every service has its own database. If a service needs a database, it has its own database, again, to improve that decoupling, right? So you're not all dependent on the same database, and so you don't get tied up with dependencies on the data set. And you can use the database technology that is most appropriate to the component. You don't all have to use a relational database if that doesn't make sense. And when you look at the world's largest and most successful applications, you think about Amazon.com, the web store itself, it uses many, many, many different database technologies depending on what the most appropriate use is. So things that, the code that builds the page that shows you, information about the product that you're thinking about buying uses a very different database to the system that does the billing for you on the back end. The third area of cloud native was dynamically orchestrated. And essentially what that means is the application now is this sort of living, breathing collection of containers. And basically everything that you would want to do in the data science world translates into starting and stopping containers. And that's the job of the orchestrator. And we're going to talk about container orchestration in more detail. But you think about anything that you might typically do, like you're going to, let's say, edit a notebook in Jupyter. What happens there is you start a container that contains Jupyter itself. You mount in the file system that has the files that you want to edit with Jupyter, and that's how you edit a Jupyter notebook in a cloud native system. And when you're done, container stops, and your files are, because they're on external storage, all the changes are persisted there. Same thing when you think about deploying a machine learning model. What's happening there is you're starting a container that contains the model, and it is now able to field requests into the API. So these might be prediction requests, and serve those responses. Right? So you start a container, you upgrade a version, you start a new container. So let's see what that looks like in terms of what the orchestrator has to do with containers to do common things you might do in data science. So let's take a look at a model. So I've built version 1 of the model. I'm very happy with it. So my container has got REST API code, the model code itself, any packages and dependencies I might need for this. Maybe this is using TensorFlow, so I need all the TensorFlow libraries, everything else, some CSV files, whatever I need, all gets wrapped into the container. And so my model is happily serving out predictions, and then I have a better version of the model, something that makes better predictions. And so the way that we do that in a cloud native way is that we start a new container that's got version 2 of your model in it, and then we delete the old container. So the new container essentially takes over and starts serving prediction requests. So we didn't go into the existing container and patch it in any way. And in fact, if you're familiar with the Linux world, where you're making essentially live patches to running systems, there is no patching in the cloud native world. And that's back to this immutable infrastructure idea I talked about earlier on. The idea is once the container's running, you don't mess with it. If you need to do a new version of the container, an upgrade, then you create a new container, delete the old one. And this enables you to scale this out and make it incredibly reliable across multiple nodes. So you get some scale benefits to this as well, and I'll talk more about those later. So here's how we scale up. Similar concept. We've got a load balancer component now, which of course is a container. But the load balancer might be something like Nginx, or it might be something more sophisticated than that. Doesn't really matter for this example. But I have my application, it's my model, it's happily serving predictions, but we reach the point where it can't keep up. We've got more requests than that container can serve in a given unit of time. And so the way we scale up is by adding containers. We start new containers. And so now the load balancer is able to pass requests to both of those containers. And now each container is able to handle 50% of the load. So we've increased the capacity of this particular model serving by 100% by doing this. And we can just keep adding containers in order to scale up. And because containers start very quickly, we don't have to preload or pre-warm or forecast in advance. These containers can start in seconds, and so we can start new containers as demand increases dynamically. And that's a big difference between using this kind of approach in a public cloud or a virtualized environment, because when you start a virtual machine, you're looking at 2 minutes, maybe longer, depending on what it is, to start that virtual machine. And so you can't really respond instantaneously to load. And essentially what you have to do is start predicting load, warming up virtual machines so they're ready to go to serve. And so this is one of the big differences and one of the between containers and virtualization, and why container-based systems are often more preferable for dynamic scaling. Same approach is now applied with a smart load balancer to do A/B testing. So here we are, we've got version 2 of my model, and I want to find out if version 2 is in fact any better than version 1. I think it is, but the proof of that is actually to have it serve some predictions and see how it compares against version 1. And so the way we set that up is that we are able to load balance the traffic, and we give a small 2% of the traffic we give to version 2, the new version, and the majority of the traffic, 98% of it, goes to another 2 containers that are doing version 1. And so I can compare the results of these two, and if container version 2, it turns out, is more accurate and is serving better predictions, then I can just use version 2. And if it's not, I can just delete container version 2 and just switch back to putting all the traffic to version 1. So that's how we can do an A/B test. This is also how I would do multi-arm bandits. Here's another example, champion challenger. And in this example, the load balancer is duplicating traffic, right? It's duplicating requests. So the current champion is version 1. And so I've got 2 containers serving out version 1. And in parallel, I run version 2. The users never get to see the results of version 2. That's just for my own internal comparison. And that's the difference between A/B testing and champion challenger. But here I can see whether version 2 performs any better or not. And if it does, I can promote that to be the champion and then repeat the process. So being able to orchestrate these containers is very important. And back in 2016, there were lots of different ways that you could orchestrate containers. There was Docker Swarm, Kubernetes, Mesosphere DCOS, based on the Mesos and the Marathon scheduler. There was Pivotal Cloud Foundry. So there were lots of different contenders, really, for container orchestration. And essentially, by using Google Trends, we can see what happened. You can see back at the beginning of 2016, all of these different container orchestration approaches were very close and real contenders with each other. But over time, gradually, Kubernetes came out ahead and essentially has become the de facto container orchestration system today. And so now Kubernetes is everywhere. It's in everybody's application. So now Docker ships Kubernetes. There's Kubernetes in Mesosphere DCOS. Pivotal has Kubernetes in Cloud Foundry. And then all of the major cloud providers all offer Kubernetes services. So Kubernetes essentially won this container orchestration battle. And I think part of the reason for that is that it came out of Google's experience in running containers at scale. So Google was running billions of containers a year way before anybody else. Google switched to containerized approach before anyone else and really pioneered a lot of this. And Kubernetes was essentially a re-implementation of into an open source project of an internal Google tool called Borg, that Google used for container scheduling. And they couldn't open source Borg, it had too many internal dependencies, but they could build essentially a replica of that, and that's what they did with Kubernetes. And they were smart enough to put it into an independent organization, part of the Linux Foundation, the Cloud Native Computing Foundation, so that it could become a thing outside of Google and independent of Google. So the Kubernetes architecture is actually very similar to many other orchestrators in the sense that there is a master and multiple masters in a redundant configuration. And the master essentially controls the cluster and is in charge of providing an API so you can configure Kubernetes. So everything you do in Kubernetes is essentially sent to the master, and it figures out what each of the minions, each of the worker nodes has to do. So the worker nodes essentially run containers. A worker node is a very small chunk of code that runs on a server, so a virtual machine or a physical server, and it starts and stops containers. And essentially the master figures out the commands that it's going to send to its worker nodes. And built into Kubernetes is things like automatic health checks and remediation and fault tolerance. So if a particular worker dies or the master loses contact with it, it will take all the containers that were running on that worker and it will reschedule them. It'll run them on remaining workers. So your application comes back up again. And it will also take care of doing all the network plumbing and everything else so that works. So there's a big advantage to using Kubernetes, and lots of things you normally might have had to code yourself into your application are now just provided for you as part of Kubernetes. Kubernetes is declarative, and it's declarative because it makes it very easy for Kubernetes to make sure that the cluster is always doing what you intended. I mean, there are two approaches to doing configuration. Declarative and procedural. And procedural is sort of like, do thing A, then do thing B, and then do thing C. But in a distributed system, if something goes wrong while you're executing that procedural approach, then it's very difficult for you to figure out what you should do differently to get to the intended result. So the advantage with declarative is that you state the intended result. And in this example here, I want 3 replicas of Nginx to run. I want Nginx version 179. I want it to serve on port 80 of this particular container. And so if something happens, say like worker node dies, then the master can see that now, a worker node has died, and let's say one of the containers in this deployment disappeared as a result of that, so I need to restart another container, so I always have exactly 3. But let's say the node didn't actually die. What happened is that we lost network connectivity to that node, and then so some short time later, the node comes back and rejoins the cluster. And at that point, I've got 4 replicas running of Nginx, and again, Kubernetes can see that I've got 4 instead of 3, and it will delete one of the containers, so we're back to 3 replicas. And so this declarative approach makes it very easy to get to accurate state in the presence of all kinds of failures and things that happen every single day in data centers across the world, like failed nodes and broken networks and natural disasters and so on. So everything in Kubernetes is a YAML file. So if you start playing with Kubernetes, you're going to have to learn to love YAML. So we've done a quick spin through Cloud Native. Let's talk about how Cloud Native differs from big data, sort of traditional big data, and the Hadoop world. And big data is essentially built on 3 tenets. It's based on Java. It's very MapReduce oriented, although you don't have to use MapReduce. That is, in fact, the way that most people use it. And it's focused on batch processing. Even real-time Hadoop is basically a series of small batches that you run continuously. So Hadoop came out of a paper that Google wrote in 2004 called MapReduce. So Jeff Dean and others at Google were using MapReduce, this algorithmic approach, to do distributed processing to compute the search graph of Google. So Yahoo, having a very similar problem with Yahoo Search, implemented their own version of MapReduce, and that became the core of Hadoop, right? So this 2005 work that Yahoo did, they built this Java implementation of MapReduce, and that's the core of Hadoop and became what we know today. So very different in terms of its emphasis and approach, and it sort of reflects the technology and the challenges of that time back in 2005. But today, in 2018, some of these approaches, just don't really fit with current reality. And one of those is being Java-centric. And back in 2005, that wasn't a problem. It was how everybody did things anyway. But now, when you've got data science code being written in Python and written in R, it's not written in Java. And the fact that you can't easily share data between the Java world and the outside world, whether that's Python or R or anything else, is a big problem. And so, for example, this is a real problem today for folks wanting to run Spark queries and do Spark processing from Python. It's like all of the data has to be serialized, sent over the wire, and then deserialized again on both ends, right? So when you run a Spark query and you get the results back from the Java world, all those Java objects have to be turned into something that can go with a wire. And the wire in this case might be like a network socket or a Unix socket or something like that. But it all has to be serialized, and then the Python code then has to deserialize that and turn that back into in-memory objects in Python. And so some of the benchmarks that have been done, say today, about 88% of the execution time is spent serializing and deserializing that data, right? So it's very difficult to mix Java things and non-Java things. The Java virtual machine just assumes everything happens inside the virtual machine. There is no sort of concept of being able to share data and information externally. Second thing is that Hadoop and the Apache universe around this also are very focused and centric on MapReduce. And MapReduce is great if you're computing a search graph. I've got an example here. This is for word counts, but it illustrates the problem very easily. So if we think about, we've got all of our data, we split it up into smaller chunks because we want to process each chunk in parallel, right? So that's why we do the splitting in the first place. So you think of the splitting as being like the Hadoop file system, HDFS, right? You're storing all of this in a distributed file system. And then the map process is the actual computation. And so what we're doing here is counting words. And so the map process is designed, the splitting and the mapping process is designed so that none of those mapping processes need to communicate with any other mapping process, right? They're completely independent. And that is how you can get the parallelized execution, and you get the performance and parallel execution that you're looking for. And that's been the big advantage of Hadoop. Once you've done the map process, in this case it's a very simple word count, then the reduction process comes when you sort of summarize that back together. And so that reduces the massive data back down into a smaller result set. In this case it's word counts. So the reason that MapReduce works at all is because the splitting and the mapping process does not require any communication with any other splitting and mapping process, and so they can run in parallel. And the problem is that modern machine learning just doesn't look anything like that. Here's an example from Google TensorFlow. So the chart on the left-hand side generated by TensorFlow, and it shows gradient descent, so training a TensorFlow model and training the different layers. And what you can see at the top there is this thing called gradients. This is information that has to be shared between the nodes doing the computation, right? And so in TensorFlow, there is this thing called a parameter server that is the component that shares those gradients in the training process. And essentially, this illustrates that not every problem fits into MapReduce very well. As it turns out, computing a search graph fits incredibly well, as you might expect. Modern machine learning, not so much. And this is why Google essentially abandoned MapReduce and moved to graph-based computation, data flow graphs. And so under the covers, that's what's going on inside of TensorFlow. It's also what goes on inside of lots of other machine learning frameworks. And it's not a good fit with MapReduce. Here's another example. This is a credit risk model for a major US bank that we worked on. And we've used a tool called Dask to parallelize this. So Dask is an open source project that we support that enables you to parallelize Python. And you can parallelize it into, guess what, a collection of containers that run on Kubernetes. So in this chart, what you're seeing is each black dot represents a task, and then the lines represent the flow of data between the tasks. So it's how they're connected together. And so this is essentially linear algebra to compute this credit risk And you can see that it looks nothing like a MapReduce chart. At the beginning, it looks a bit like MapReduce because you've got a long line of dots in parallel, right, and all this data fanning out to all of those things. And then beyond that, not so much. It's quite a complex graph. And so MapReduce just does not fit well if you're doing this kind of computation. And the reason that matters is because the big advances that we're seeing in AI require a lot of compute. You must be efficient. This is a chart from OpenAI, and they looked at how much compute is required, how many petaflops are required every day to train the leading AI models. And they looked at lots of different models from people like Google and OpenAI and others. And so what you can see here is that back in 2013, you're looking at 0.01 petaflops a day to train some of the leading models. And then in 2018, AlphaGo 0, so Google's AI algorithm for playing Go that's beaten various Go masters, requires 3,000 petaflops per day. So that's a logarithmic scale on the y-axis there. So it's 3,000 versus 0.1. So you've had this enormous growth in the number of petaflops required to train these models. And essentially OpenAI's conclusion is there's a 10x growth per year in the petaflops required to train leading models. Now, good news is it's not 10x the cost because things like GPUs and TPUs have made this economically feasible. But you cannot afford inefficiency if you're going to be a leader in AI. It's very important. So Anaconda's data science platform, Anaconda Enterprise, is an example of a cloud-native application. When you install Anaconda Enterprise, effectively what you're getting is a Kubernetes cluster with Docker running containers. And the containers are our application, Anaconda Enterprise itself, the user interface, authentication, documentation, storage, and so on. But also containers are used in order to do things like run editor sessions and run deployed models or deployments. And so this is an example, a simplified sort of view of the application as it's running. And then if you think about a multi-node AE5 deployment, where you've got multiple servers, perhaps multiple masters for redundancy, and then multiple worker nodes for scale, you can see that essentially those containers from that previous diagram are essentially distributed across those different nodes, and this is how you scale up Anaconda Enterprise. So for Anaconda Enterprise itself, a simple model, let's keep it simple and say our model is deployed inside of a single container. This is how it works. API request comes in, we have a proxy container that sits in front of every model. Every deployed thing has this proxy in front of it. And the purpose there is to enforce authentication, right? So you want to make sure that you can control who has access to this model, who can send requests to it. And so guess what? The proxy is a container, and then it makes an API request to the authentication service. So network API call to the authentication service to see if there are valid credentials being presented. And then if they are, the proxy container passes on the API request to your container running your model, gets the result and feeds it back. And if it's not authorized, then it'll just send an error message back to the caller. So you've been able to apply these cloud-native principles to a model deployment. And also now we can make this model deployment scale. We can have multiple containers serving the model. We have multiple containers serving the authentication service, for example, if we get lots of load. We can scale this entire thing up, and we can run it in parallel in a large cluster. We can take advantage of as much compute as we want to. So what I've done today is show you how you can accelerate your data science lifecycle with Cloud Native. We've talked about what Cloud Native means, and we've also talked about how it can help you grow and scale and go around this loop more quickly. Collect your data, visualize, model, test, and deploy, and do that much more quickly. Do it upgrades, non-destructive upgrades, and be able to grow and shrink your models and your application with scale. Thanks very much.
Thank you for walking us through all of that, Matthew. That was incredibly informational, and it was a great way for us to really learn about what the cloud native space looks like today, the benefits that it has had for companies scaling their infrastructure, and more importantly, how we can apply those things to machine learning pipelines in today's fast-growing organizations. So if you want to learn more about Anaconda Enterprise, please reach out to us. You can learn more at our website, anaconda.com/enterprise. And you probably want to see Anaconda Enterprise in action. So schedule a demo by emailing ambassador@anaconda.com. And we also have some other offerings like consulting, training, and support, for which you can email the same email address, ambassador@anaconda.com. Again, thank you for joining us, and we hope to hear from you soon.